Okay, so it's preparing to stream right now. So Jim, if you'll go ahead and get started.
Okay, I'm going to share my screen. Let's see if I can be not that guy that does this. Okay, can everybody see this? Can everybody see the intro slide? You see it? Okay, good. All right. Thank you all for, I'm really enjoying this. I just joined a couple weeks ago and I'm really enjoying this chat, talking about all sorts of interesting things that are very interesting to me. I've been in the HMD design business for about 35 years. I've designed probably 20, maybe 30 HMDs for a variety of applications. Very interested in the design hardware itself, the human factors, both perceptual and auditory, anthropometry. Pose and gaze tracking is very interesting, and also how we can use bio-inspired design to implement, to influence sensor design, and also tracking. As it turns out, obviously the animal kingdom is a lot of things that we can learn about tracking. So early HMDs, head-mounted displays, and I'll use the term HMD. I know people use the term smart glasses or near-eye displays or VR, AR, things like that. I'm going to use a very generic head-mounted display. Most of them were originally for military applications because the military had the need and the military had the money, because quite frankly, at that time, things were very expensive. The very earliest that we have was the U.S. Army put one on their Cobra gunship in the mid-70s. It was just a little targeting reticle. In the mid-80s, the Army put that on their Apache the iHads, and the Russians, the Soviet Union, actually put it on their MiG-29 a little bit. And that, when it came out in on the MiG-29, of course, the Israelis decided they were going to have to do something because they are very proactive people. But about that same time in the early 90s, the early virtual reality actually started. We had a lot of effort going on, and that was about the time when Jaron Lanier coined the term virtual reality. But unfortunately, the technology was just really big and ugly and clunky, and the resolution was really poor, and the computers were slow, and it really failed in the early times. So it's very heartening, I'm very pleased to see that the technology is gotten to the point and the costs have dropped and things like that, where we can do something. And you folks on the call here are doing some really interesting things with it. I think it's just really a wonderful thing. What I'm going to try and do today is to give you just the benefit of some of the mistakes that I've made. I don't say that I've got more experience necessarily, but I will guarantee that I have made more mistakes than all of you at any given point. And so that's really the idea here. First and foremost, the idea is to really understand what it is, the application. I think there's, right now we're not at a point where we have the one single head-mounted display that's universal for everything, because the application, the task at hand, all of the rest of this is really going to focus what we do and define the requirements for what we're going to do. And secondly, we really need to understand the human factors aspects. Where you're putting something on. You're putting a piece of hardware on one of the most complex pieces of biology ever, the human head. And so we really need to understand the visual and auditory human factors, anthropometry, meaning where things are, how things fit, our head neck anatomy, so we know where to put the weight, and also sociological. I mean, there's a great example with the Google Glass where they went and did some interesting things with the Google Glass, but they didn't understand all the sociological impacts, and therefore we ended up coining the term the glass hole as a result. So really, I can't emphasize enough matching and understanding your new users' needs and tasks and matching that to the hardware. So let's start with the first one. About 1985, we started working on a project for putting a helmet-mounted display on a fighter pilot. And unfortunately, as in most instances, if an engineer designs something, it looks like an engineer designed it. and it's just really ugly and bulky and things like that. And the pilots just didn't like it because aside from being very, very good at what they did, they also have very large egos. And so they weren't going to put something on their head that made them look bad or not, whatever. So enlisted the aid of an industrial designer by the name of Peter Ronzani. Pete Ronzani worked on the Star Wars films. And you see in the lower left there are some of his sketches. And if any of you are a Star Wars fan, you can kind of see where the heritage lies, where some of that comes from. And Pete was able to help us bring to fruition the very first helmet-mounted display that I did, called the Agile. It was a 20-degree circular field of view, monocular, right eye, monochrome green. Very simple, but very effective, and really, the pilots really enjoyed it, especially after we let Peter Ronzani get a hold of it and really make the thing look really nice. And so you see that in the upper right-hand corner, the photograph there. Secondly, the next one was one that I worked on for the U.S. Army, was for a helicopter program. And this was a wide field of view. And I use the term wide field of view to some people may mean much larger than this, but 60 degrees was a revolutionary number at that time. And we did it by using partial binocular overlap to get that. The first time we used it in the simulator, we caused a lot of eye strain for the test pilot that was flying it. We flew it for about 4 hours or so, and he just absolutely loved it. He just thought it was the greatest thing in the world. And he just flew it and flew it and flew it and good. That night he woke up with very, very severe headache from the eye strain associated with this. And needless to say, we got called on the carpet. I got called on the carpet by the management to say, what happened? What did you do wrong? Why did you do this? What happened to our pilot? And after some serious investigation, we discovered there were two things that happened. Number one, they put the symbology out at the outer edge of the field of view. So the pilot, and if any of you are pilots, you know that you're taught to scan. You look around at your instruments on a regular scan pattern. And so what the pilot, being a pilot that he is, did his regular scan pattern. He looked at the symbology across the field of view. Down at his instruments, looking outside, went back and scanned the instruments, the imagery in the field of view. The problem was that because they put this symbology at the outer edge, it required the pilot to scan plus or minus 30 degrees. That's more than the nominal plus or minus 15 degrees that we as humans like to do. Anything more than plus or minus 15 degrees, and it makes you want to move your head. I mean, yeah, I can see Andrew. I can see you moving your eyes around like that, and I do the same thing. Okay, imagine doing all the way out at the edge, all the way out at the other edge, and then doing that for 4 hours. You can feel a little bit of tugging in your eyeballs. Okay, so they had to redo where they did that symbology. The second thing, and this is something that's really, really important, is binocular misalignment. It's something that is really, really critical, especially with see-through augmented reality type displays. Really no more than 3 to 6 arc minutes in the vertical, and horizontal 5 to 10 arc minutes relative to what you want to align it to, and make sure that you're plus or minus a quarter diopter in focus. So the focus and vergence agree with each other. If anybody wants to talk about that one more, I can talk about that one at length. But this was so the lesson here is to really understand, again, here we focus on the human factors issues. What is it that we humans normally do? How do we normally behave in an environment, to make sure that you're not going to make them do something that the human is just not capable of doing? And you can see, also that Peter Ronzani got a hand in the paint scheme of the helmet that we came up with. So he got some good work there. About a year later, we took that helmet and we flew it in an Army helicopter, the U.S. Army's Apache helicopter, and that's actually me helping one of the pilots get in and get installed there. And one of the things that we were using was a magnetic head tracker. Well, we didn't know that, and I don't know if you can see but right in the upper part of this cockpit structure, there's these power bus bars, and they get activated once you turn the helicopter on. But we didn't know that. I mean, we didn't know what we didn't know. So when they turned the helicopter on to fly it, suddenly the magnetics went crazy, and the imagery started spinning around, and the pilot was getting disoriented and had to, we had to shut it all down and say, what do we do? What do we do here? So we had to go back and recalibrate the whole tracker system with the power on, so that we could take into account the electromagnetic effects of the tracking of the platform in looking at our tracker. So the takeaway lesson here is really make sure you understand the platform and the environment that you're integrating into, and it's really, really critical. So otherwise, so you don't have an embarrassing situation like this. So this is another military program, took place about the same time, early 90s. The U.S. government, the U.S. Air Force wanted to have an ejection-safe night vision system, and what you see here is a system called the iKnights or Strike Eye program. And the thing to note here is that there's two sensors that are outboard sensors, separated by about 10 inches. And the human eye separation is approximately 2.5 inches. Well, the problem, and the reason they did this was because the packaging. You had to get the optics and everything inside there, and putting the sensors outboard is just a really convenient place to put it, get it away from the face and all the rest of that. And so the problem was that the 10-inch separation creates what is referred to as a hyperstereoscopic effect, false stereo depth. And so the pilots, when they were landing, they were actually landing long. So because they thought they were actually lower, the stereoscopic depth brought the imagery in from the landing. This was from one of our test pilots, one of our employees who went out and flew it one night. And he said, there's something going on here, I'm not sure what. And again, had we paid attention to the human factors issues when we did this, we probably wouldn't have had this issue. But it was a fun program nonetheless. All right, next one. Now this is one of the first commercial ones I worked on. This was the QView. This is shown at the Disney's Epcot Center about in the early mid-90s. And what it was you looked as though it was a virtual pool game, and you were the cue ball on the pool table, and each of the cue balls looked like they were 10 feet diameter. So this was you were this huge cue ball, and you could see the guy's got the little controller there, and what it does, he would push the button and it would raise his viewpoint up so he could look at the table and figure out where his shots were, and then he'd let go and it'd come down. You push a button and it would shoot the balls forward, and you would play a pool game, a virtual immersive pool game. It was great fun. We had a lot of fun playing that, setting up that game and playing with it. This was a 100-degree by 30-degree field of view, pretty good for that at that time for the early 90s. The problem that we had was that we just couldn't. The computer systems weren't fast enough at the time. I mean, I've probably got more processing on my cell phone right now than we did at those computers. Between that and the games it was just too expensive to be able to put these things out. But as I said, we did get a few out in the field, and then as you can see this from the picture here, they were having a good time playing it, as we did. So this is one that worked on about mid-90s. This was the Vista Medical HMD. Vista Medical was a company here in Carlsbad, California, that was a spin-off of our company, and they were trying to develop a head-mounted display to assist in minimally invasive cardiac surgery. So what you see here is the Vista Medical headset. You see the hoop headband with the displays, and the intent here was that the surgeon would take that imagery, would view the imagery from a binocular stereoscopic endoscope and go into the body cavity in between the rib cage and actually do work on the beating heart, do heart surgery, replace a valve and things like that without having to crack the chest. which was a really, the first initial results were very, very promising, because for the patient, I don't know if any of you have had someone go through that. My mother went through it, and she couldn't lift anything for basically 5 months. She couldn't lift anything, just because the sternum is cracked and you can't move. So this was actually the first FDA approved HMD for minimally invasive surgery. The problem was that it takes 7 to 9 years to train an endoscopist, and most heart surgeons in their 40s and 50s, who are at the height of their career, making a boatload of money, doing really well, they didn't want to accept the fact that they would have to go back to school and learn, take 7 to 9 years and retrain. So this is for this particular application, the cardiac surgery, it did not succeed. Although they did go into other things like bariatric surgery, things where the surgeons themselves were very endoscopic. They were trained endoscopists. But it was again, this was a lot of fun, and a lot of interesting things we learned from this. Okay, this was one of the problems that the NASA had in the early days of the space shuttle, was that the astronauts were getting sick in space. They call it space sickness, and turns out it's a combination of the visual and vestibular systems not being in sync, and all the rest of that, with the gravity and all that. So they wanted to fly an immersive head-mounted display on the space shuttle to investigate this, and so we developed an HMD with an adjustable field of view. This had just two position. The oculars would adjust to different positions to give you an 80 by 38 and a 50 by 38, and they would just click into position with some really very sophisticated mechanical stuff that our mechanical guys did. And then it had a fully immersive cover that would block out all visual cues, and so that they were trying to do some testing on the astronauts when they were in space. So they weren't as concerned here about weight and center of gravity, because in space there is no weight. Weight is not an issue. However, mass moment of inertia is a concern. The mass moment of inertia, so they found this initially when they took it up and tried it on what those of you may have heard the term the vomit comet. This is a big 747 that's empty in the back, and they basically do these long circular parabolic dives, and they get people achieve weightlessness for 20 seconds or so, and they were able to find. So the weight and center of gravity didn't matter much, but the mass moment of inertia, if the astronaut turned his head or her head, they would actually keep moving. So that was kind of interesting to try and bring that in. The second thing is that because there is no gravity in space, convection does not work. So the heat sinks that we had for the backlights, the LCD backlights at the time were very hot, and we needed to get the heat away. So I just naturally put on some heat sinks. Well, there's no convection, so the heat would just stay right there. So we ended up having to put little tiny fans on each one, mount the little fans on each one before it went up. So the takeaway lesson here is to really understand your user's operating environment. What is it they're really doing, and what is it they're really, even if it's out in space. So it's a really interesting kind of takeaway lesson. The final version is one we worked on. This was the U.S. Army's Land Warrior program. They wanted a navigation and information aid for the ground soldier. This was started about the year 2000. And basically it was early GPS, put a GPS dot on a moving map. Those of you who are, there's more sophistication on my cell phone with the Uber app now, that I can actually see where the Uber is, when the Uber is coming. But this was a big thing 20 years ago for the Army to be able to put this on there. And I actually spoke to a young captain who actually dealt with this in the field, in theater, and he said he hated it for certain things and he loved it for other things. It was a very heavy system. It weighed about 12 pounds altogether, but he said there were certain things they would only do if they could carry this with them, which really says that must have been a huge advantage that they had to be able to take this out of the field, see where they're going, see where all their guys are going, because the commanding, the sergeant or the captain, the young lieutenant, would be able to see where his people were at any given time on the moving map, so they wouldn't get lost. And so that was a real game changer. The one thing that issue that came up was that we were getting these HMDs back from the field that had a little arc in it, and what it was these soldiers would take the helmets off during a break, and they would inadvertently point them up at the sun. Now, when you point them, those of you who burned ants with a magnifying glass know that you get a lot of light concentrated from an optic, and what was happening is the energy from the sun was focusing on the LCD surface and burning the polarizer. So I ended up having to switch to an OLED, which doesn't have a polarizer surface on there. So the takeaway lesson here is really understand what the user's environment, how they're going to behave and interact, and what does it mean for the hardware. So you don't have to try and figure out how to retrofit a bunch of systems in the field because they're pointing them at the sun. So in summary, I just want to summarize really it's understand what is really what the user is really planning to do, whoever that user is. And it doesn't matter whether it's a pilot or a soldier or a surgeon or a gamer or somebody like that who's going to be using it. Really spend some time with them in watching, observing them. Have them put your hardware on and use it, and just stand back and observe. Watch the way they use it. It's really, really critical that we understand the operating environment and what they're planning to do in the ecosystem. And then understand all the human factors. If you don't understand the human factors, you might do something that's going to make them uncomfortable or cause eye strain or neck strain or something like that. And then again, I mentioned the issues with the sociological impact. I think that's really critical, that especially if we start to take this out into the field. And the metric I always say is what would your mom do with this? Your mom or your dad or your grandparents, would they really be able to wear one of these things and get away with it? And again, match the hardware and software to the environment. Does anybody have any questions?
Yeah, so thanks, Jim. I was interested in the medical application, and you said the doctors resisted the idea of going back for retraining. We clearly have had multiple chances at surgical robots. What do you think was the difference between successful adoption and this? Because the retraining issue wouldn't have changed, would it?
Well, I think what they've been able to do is to the ones that I've observed, and I can't remember the name of the company that does this. The way it was explained to me was they were doing microsurgery, and for the one application I observed was these docs who were doing microsurgery under a surgical microscope. And so they're used to they've got the hand-eye coordination developed to the point where they can actually go in and do all this stuff. And they're used to working under a microscope, but now they're using it in the machine, the hardware, the robot, if you will, is actually doing things like guiding the surgeon's hand here. They're taking out if the surgeon has too much coffee in the morning, their hand might be shaking a little bit. And what this thing does is it takes out a lot of that high frequency noise that we observe. There's a lot of other things going on too, where there's a big push now, and the Augmetics is a company that we're seeing. I've seen a lot of work recently where they're actually looking at doing an AR overlay on the patient, where you take a CAT scan or an MRI and you actually overlay it on the patient. A young doctor I was speaking with a couple of years ago was saying, it takes him about 30 seconds to figure out where the screw is to put into the body, but it might take him another half hour just to make sure because he's got to overlay he's got to look between the CAT scan and the X-ray and the patient and make sure he's palpating properly. If you can overlay that information, I think it might be very helpful. So I think I mean, that's a long answer to what was probably a simple question, but I think there's a lot of human factors, you know, hand-eye coordination issues that we have to address. You know, and more perhaps specifically to your point, is the application that we're talking about, is that particular surgical technique, is that appropriate for using with an augmented reality display? You know, as I said, the surgical application, they did some bariatric surgery. Okay, bariatric surgery is typically done endoscopically. The docs who do it are trained. Laparoscopic cholecystectomy, gallbladder surgery, they're trained with that. So there was no lag time, no training time associated with it. So I'm thinking that's probably where I think this is gonna end up going.
Okay, so if I can just kind of read that back in more market-oriented terms, a replacement product was not sufficiently, this replacement product, the original thing, that replacement product was not sufficiently compelling to cause someone to go back and redo the training. But for something like microsurgery, which is essentially a new adjacent market, because it could actually do the microsurgery in ways that were just completely unavailable to surgeons before, there was essentially, it was a virgin ground. Is that a reasonable summary?
Yeah, I think it is, and plus now they're actually taking them into the medical schools. You're starting to see them show up in the medical schools and in their residencies. So when these docs are actually training, they're actually training on the hardware. So there's it's a reach back into to get these docs early in their training careers, rather than waiting until they're 55 or so and say, oh, you have to go back and retrain now. So I think I think you're right on point there. And I think it's also being able to reach back and get these younger docs and get them trained early on.
Yeah, the obvious issue here is that if the best practice is the medical schools in general are going to teach best practice, and if the best practice isn't robotic, then it's hard to break in. And so this is not a criticism. I'm just trying to understand the dynamics of this, that, as you look at new product introductions, there's lots of morphologies of failure. And, this kind of inability of replacement product to overcome the status quo is pretty standard. So I'm just curious.
I agree with you. I think there's this is an area that I'm kind of getting into at the moment, and a great question. I don't have a really solid answer for you, Carrie. No. Let's have this conversation again in 6 months, and I may have some other ideas.
Yeah. So the real thing that caught my ear, Jim, in your description was just when you said they resisted the retraining, and that doesn't match my experience with a lot of this medical technology. So that was just the part that was just a discordant note.
Oh, I see. Okay, I see. Okay, I misunderstood. Okay, then the issue there is in this particular instance was that you can use this technology and you can do this surgery, but you can't do it for 7 to 9 years from now, because you are not a trained endoscopist. You're a great surgeon, but you're not a trained endoscopist. And so for that particular narrow niche application, it wasn't you couldn't convince these folks, these docs, to go back and basically start from scratch. I think I hear what you're saying. I hear what you're saying on the point there, but I think what it was, but like I said, they took that same technology and went to bariatrics, and bariatrics are, so I think there's like I said, it's a definition of the I think it's a definition of the task up front, matching, can we take the surgeon and take them out from a microscope and give them a head-mounted display? Yeah, probably, because it's a more comfortable to sit. You know, you can kind of sit like this or sit like this. You don't have to sit hunched over a microscope for any period of time. So I think that's really the takeaway message on that.
So one last question: are there any regulatory safety regimes that you have to overcome? So, for example, in automotive, there's a whole in many regimes. There's a whole standardization effort that's associated with trying to predict safety, and it's really a difficult thing to do. Are there any in medical? Are there any agencies that are trying to assert themselves that way?
In terms of medical, I believe the FDA is the one that's really taking the lead on that.
But so, do they have standards that talk about it? I mean, again, you know, just going back to other industries, there's specific standards you can go back to as sort of a safe harbor to say, if you've done this diligence, you have established safety according to whatever the best practice is at the time. And that's one of the issues with these kinds of highly specialized interactions that's likely to come up.
That's a great question, and quite frankly, my data dates back 30 years, so I'm 25 years. So I'm but again, starting to work on a project in that area, and let's have the same conversation in 6 months, and I'll see if I know some more by then.
Okay, great, thanks.
Yeah, does anybody else have any questions?
Yeah. Hey, Jim, this is Kaz. We spoke on the phone a few weeks back. The model that you showed the captain in the Army, besides the GPS functions back then, what other use cases did they love using it for?
Unfortunately, he couldn't discuss too many of them because some of them were above my clearance grade. But it's the system itself basically was designed for basically a GPS. You know, I've got the same thing on my phone when I use MapQuest or Google Maps or something like that. And that's basically what it was a hands-free navigation aid. So the platoon sergeant could see either a blob where the center of mass of his people were, or he could look and see where they were individually at any given time. So it was primarily a location and navigation, or they had a little handheld keyboard and they could actually type in text messages if they didn't feel like they could communicate verbally, or they didn't want to communicate verbally for some reason, they could actually type in text messages. So again, a lot of stuff that I have on my cell phone right now, which is, but it gives you at that time it was a major step forward, because cell phones just weren't that good at that time.
And besides the weight, what things did they not enjoy about it?
The weight, the batteries are a big deal. I mean, if you have to carry your power, because it is, quite frankly, that's the other thing is we were using the technology at the time was the processors, the GPS, the radio, the display. All of those things took up a large amount of power, and so the batteries were very heavy. So it was not just the weight of the system itself, but it was the weight of the batteries that they have to carry, and that's a big deal with anybody. We find that with first responders have the same issue. They're reluctant to carry any more weight than they already do with their helmet and their oxygen and their coats and their boots and their axe. Put some more weight on these folks, and they get really bent out of shape. So I think the overall weight is something that we have to address at some point. Plus at that time I've got this great picture of these guys coming back from a training mission, and the batteries had spontaneously caught fire and basically melted everything. So that was to see this big lump of melted nylon fabric. That was pretty interesting. But I think overall cause weight was a really big issue with these folks.
Still is.
So yeah, Jim, great presentation. I did have a question about the binocular versus monocular range on some of the headsets. Did that cause any problems with the user's interactions with the information?
Yes and no. I mean, there's a huge effort right now dealing with symbology in aircraft, binocular symbology in aircraft. Do we put symbology? Do we present binocular symbology, or do we present monocular symbology in a binocular display? The Air Force has got there's a group of folks out there at Wright-Patterson Air Force Base who are working on that issue right now, and quite frankly, it's going to take some time to sort this one out. I think it's a really great question. I think where you put the symbology, how you format the symbology, how you format the information, you really want to, the idea for a pilot is to reduce their cognitive workload. You want to make life easier. In the same way, my truck has an analog gas gauge, and I have to always think about how many more miles have I got on my half a tank, and a gallon, 47 to carry the 3, or my wife's car, which it says you got 13, you got 143 miles left on your tank. I think that all of that those are issues that I think that we're going to work out over time. And I mean, that's what you folks, those are the kind of questions you folks should be asking all the time.
See, does anybody else have any other questions?
Yeah, I have one about the controllers. So, like, are you seeing any move towards standardization of controllers coupled with the headset? Because a lot of it now seems very confusing as to how you program and hook these things up.
The controls tend to be very, very user specific, user task specific. So let's say, a pilot in a biz jet. One of the things I worked on recently was how do we make the changes to the imagery, the symbology for the pilot versus the doctor versus the first responder or the firefighter. How do you make those? They're very, very, they tend to be very specific to the task at hand, and you want to be able to give them the option of quickly turning it off or minimizing the symbology at any given time. Because I work with folks who are typically in high stress environments, and one of the big things we found is that we have to be able to minimize the symbology. Take it down to its bare minimum at any given time, and that may differ between two pilots. So we let these guys go out in the field and set it up on their own, and it turns out some of them like one set of symbology, some of them like another one. They like a hybrid, something in between. But really giving them the option of being able to do that and control that themselves is really a big deal. I hope I answered your question.
Great, thanks. Does anybody else have a question? All right. Well, thank you, Jim. That was a terrific presentation. Really, really fascinating. I'm going to stop.
Just uploading.
Yes.